So today, the second method of solving a system of equations, the substitution method. This is all algebra. If you are good at solving equations, this is for you. If you are not good at solving equations, you will hate this. The best time to use this one, as it says here, the best time to use this method is when a system has at least one equation that can easily be solved for one of its variables. What that really means is a variable has a coefficient of 1. That is a better description. When a variable has a coefficient of 1, this is an okay method to use. I don't really want to go through these steps. They're more for your, I'm going to read through them quickly, but you won't remember them. So we'll do them as we do the examples. The first step is solve one of the equations for one of its variables, like get the variable by itself. That is the first step. One of the equations, get a variable by itself. And then substitute that amount into the other equation in place of the variable. I'm going to do it for you in a sec, don't worry. Okay. I know it's hard when you see the words and you don't do an example at the same time. And then solve for the other equation for its remaining variable and resubstitute. Let's do it and I'll show you how it works. Here we go. So in this first example, step 1 is get a variable by itself. And in this first example, there is a clear winner. There is a variable that you should definitely get by itself. You know, you got 4 choices. I could get the y in the first equation by itself. Or I could get the x in the first equation by itself. Or I could get the x in the second equation by itself. Or I could get the y in the second equation by itself. You know which one is the clear winner, Boyer?
The second y.
Yes, the second equation, y, because it meets this description, a variable that has a coefficient of 1. Why is it good to get this y by itself? You're not going to have to divide by anything because it doesn't have a coefficient. Like if I want to get the x by itself, I'm going to have to divide by -2. That's going to cause fractions a lot. Or here I might have to divide by 3. That's going to cause fractions. 14 divided by 3, that's going to be a fraction. When there's a coefficient of 1, no fractions. So, what would I do to get the y by itself in the second equation? By the way, I like to draw a line down the middle like that. I would add 2x to both sides, right? All I would do is add 2x to both sides. So plus 2x, and I have y equals -3 plus 2x. All right, step 1 is get a variable by itself. All right, that's what it showed right here. Step 1, get a variable by itself. Step 2 is to substitute that amount into the other equation. Watch this. This is why they call it substitution. Take what y equals. Here's what y is equal to. It's equal to -3 plus 2x. Take that and substitute it into the other equation in place of the y. Now that I know what y equals, I can replace the y with what it equals. So I'm going to rewrite the other equation, but I'm going to replace the y. And the other equation would now be 3 times, instead of 3 times y, 3 times that amount, -3 plus 2x. Plus 4x equals 14. All I did was replace the y with what y is equal to. We okay with that? Okay, if you can do that, that's the hard step. From now on, it's basic stuff you know how to do already. Go ahead and solve this for x now. We'll play name the next line. We'll start with Noah. Noah, give me the next line to solve this equation.
-9.
-9, great.
Plus
6x
Awesome.
plus 4x.
Awesome. He gave me the next line. Ashton, give me the next line.
Negative 9 plus 10x.
Nice. Give me the next line, Gunner.
10x equals 21.
Ooh, do you guys know how he got 23?
Oh, yeah, 23.
He did what?
He added the 9.
He added the 9 to both sides. Do I need to write down plus 9 plus 9?
Yeah.
Okay, if you're a good solver, you do not need to write that down, plus 9 plus 9. You can just go straight to 10x equals 23. And then what should I do?
Divide by 4.
Do you know what that gives me?
2.3.
X equals 2.3. I now have the x value. That is half of the ordered pair that is my solution to this system of equations. How do you think I get the y value? Well, it says back here, solve the other equation, so I solved it and got 2.3. Now, re-substitute back into the first equation to solve for the other variable. Well, now that I know x equals 2.3, I can go ahead and substitute it back into the other equation and get what y equals. Y would equal negative 3 plus 2 times 2.3. Now I'm just doing arithmetic. Let's see, what's 2 times 2.3? Is that about 4.6? And what's negative 3 plus 4.6? Is that about 1.6? And I have solved the equation. I've solved the system of equations. And if I graph these two lines, you know where they would cross? Where would they cross, Nate?
Right there.
Would that be an easy point to tell where the lines crossed?
Definitely not.
No. All right. We all good with that?
Mm-hmm.
Okay, that is about as hard a one as you could possibly have. It's about as hard as you could possibly get. These next two, much easier. Why are the next two easier? Nate?
One already has a variable by itself.
Already got a variable by itself. You know, this is really the only time I use the substitution method, when it's already got a variable by itself. Otherwise, I would not have done that one by substitution. I would have done that one by the next method we're going to learn. Friday. The elimination method.
Yes.
Nah, you might not learn it Friday, actually. I'll talk about that. Anyway, here we go. I'm going to draw a line. I think we're going to have Melissa tell me what to do. Step one is done for you. You have a variable by itself. What should I do? Substitute. Yeah, what do I do that? How do I do that?
X plus 3x equals.
Nice. So she took what y equals and she substituted it into the other equation in place of the y. And now we're ready to solve. Ryan, what's the next line?
Negative 32 minus x equals 3x. What?
Maybe. I mean, that's not wrong. That would be true. Negative 32 minus x would equal 3x. But Ryan, I'm trying to solve for x.
For x.
Feeling a lot of pressure now, aren't you, Ryan? All these people raising their hands. You want me calling somebody? James?
4x equals negative 32.
Add your like terms together. 4x equals negative 32. Hannah?
X equals negative.
If you like algebra and solving equations, this is the method for you. If you can just whip through things like that, it's a good method for you. What do I do with that answer then, Ethan?
Where?
X equals negative 8. What do I do with that?
You put it back into the other, yeah.
Put it back into the other
Yes.
equation.
Yeah.
And so y equals 3 times x. But instead of y equals 3 times x, it'll be y equals 3 times that. All right? I'm substituting it back in for x in the first equation. And that would be y equals negative 24. And now I have my ordered pair, negative 8, negative 24. Ba-bam. One of the most common times to use this method is when both equations are already in what would be slope-intercept form. But you don't want to graph them, because when you graph them, sometimes you get a bad answer, like 2.3, 1.6. You just like the substitution method better instead of making a big graph and trying to see where the lines cross. So all you would do is take what y equals and put it into the other equation in place of the y. So instead of y equals x minus 1, you'll have 2x plus 7 equals x minus 1. Aria, what's the next line?
Would you subtract 2x?
I wouldn't.
I mean, okay.
I'm not saying you can't, just not what I would do.
Would you subtract x? I don't know.
That is what I would do.
Okay.
What would that give me?
X plus 7
She got it. See how she subtracted 1x from both sides? Right? And then what would you do there, Summer?
Oh,
Or just give me the next line.
x equals negative 8.
Subtract 7 from both sides. And you have got the x value. And now you're ready to resubstitute back in the first equation. So instead of 2 times x plus 7, it'd be y equals 2 times negative 8 plus 7. And what's 2 times negative 8? Is that negative 24? No. It's negative 16 plus 7. And what's negative 16 plus 7? Is that 13? No. Is it 149?
No.
No. Is it negative 9?
Yes.
Yes. And you now have the solution to your system, right?
Right.
Okay, let's look at a couple other things. Okay.
I like this.
A common application for system of equations that can be solved using substitution is when the cost of some items and the number of items are both given. Cost and number are both given. Let's see an example. A snack bar sells 2 sizes of snack packs. A large snack pack costs $5 and a small snack pack is $3. In one day, the snack bar sold 60 snack packs for a total of $220. So the total number of items was given. They sold 60 of them. And the total price was given, $220. This is a common time that you'll set up a system and figure out the answer. So, listen, I've got you doing, I think there's only 7 or 8 problems on tonight's homework. 2 of them are like this. Okay, the key to this is, first, you must define variables. Okay, have your variables be the answer. 98% of the times when you define a variable, it's the answer to the question. The question here is, how many small snack packs did the snack bar sell? Shoot, not a great question. So I'm going to have x be the number of small sold. But I need a second variable because we're dealing with 2 equations, 2 variables. So I'm going to use y also. And I didn't ask for this in the question, sadly. I wish I had. But what do you think the other variable would be then, Nate?
Number of bigger bags.
Number of large sold. Okay. Well, you know 2 things about these snack packs. You know the total number and the total price. Can you set up an equation for each? What would an equation be for the total number? 60 snack packs were sold. What would my equation be?
X plus y equals 6.
The number of small plus the number of large equals 60. what would an equation be that deals with the total price? Nate! You're on fire today, Nate. Yes?
5x, no wait, 5y plus 3x equals 220.
3x plus 5y. 3 times x is the cost of all the smalls. 5 times y is the cost of all the larges. And we know that adds up to $220. In the interest of time, I'm not going to solve this. I will tell you the first thing that I would do is I'd get the x or y by itself, like maybe I'd get the y by itself by subtracting x from both sides. You follow that?
Yep.
And then I would take what y equals and I would substitute it in for y and I'd be on my way to solving, right? Okay, I'm not going to do it. I want to show you one or two more things. It is possible for a system to have no solutions, right? When you graphed, you got no solutions when the lines were parallel, or infinitely many solutions when it was the same line, right? The same thing happens when you're solving by substitution. You might get no solution, or you might get infinitely many solutions. You get infinitely many solutions if both variables cancel out and you're left with something equal. Both variables cancel. If both variables cancel and you're left with something that's equal, no solution. If both variables cancel and you're left with something that's not equal, no solution. So let me give you a quick example of that. I'm not going to do the first one. It looks too hard. I'm going to do the second one. I'm going to take what y equals, and I'm going to put it in for y. So instead of y minus 3x, I'll have 3x minus 11 minus 3x equals negative 13. Ryan, what happens when I simplify the left side?
You have to cancel out the x's and make them 1.
The 3x and the minus 3x cancel out. That'd be 0. And I'd just be left with negative 11 equals negative 13. This would be an example of what might happen when you do substitution. Both variables canceled out, and you're left with something that is either true or false. True means they're the same line, infinitely many solutions. False means these are parallel lines. There's no solution. This one has no solution. As if those lines, if you graphed them, those lines would be parallel. That makes sense? I have one more slide. Let me see what it is. If you look closely, a lot of times you can tell in advance if there will be one solution, no solutions, or infinitely many solutions. Okay, I talked about this today a little bit. Guys, look at this. What happens if you multiply 2 by negative 3? You get negative 6. What happens if you multiply 7 by negative 3? You get negative 21. And negative 4 times negative 3? Do you see how this equation is just the first equation times negative 3? When everything is a multiple of the other, it's the same equation. When everything is a multiple of the other, it's the same equation. And what does that mean? If they're the same equation?
Infinite.
All right, means infinitely many solutions. What happens if just the variables are multiples? Times 2. But the number is not a multiple.
No.
That would be two equations that would be parallel. Be no solution. Kind of rushed through that. We'll talk about it more